My name is Michael Bretti, and thank you all for tuning in to listen to this talk, and thanks to Alba Orbital for this amazing workshop that they put on. Today I'm going to be talking about my work on low-cost ionic liquid ion source electrospray thrusters for PocketQubes through my startup AIS. So for those of you who don't know me, I'm the founder of Applied Ion Systems, and as far as I'm aware, it's currently the only independent maker-based at-home R&D program for plasma and ion thruster development. So everything is done quite literally in-house and supported, out of pocket and through donations through the AIS Patreon. And really the goal is to develop ultra low cost, easy to manufacture and open source thrusters, as well as providing resources for the nanosat community, for the hobbyists and educational communities out there to really lower the entry barriers of entry into this field. So getting right into the basics, principles of electrospray, conceptually it's a very simple type of system. You have a liquid fuel that is either actively or passively fed through some capillary or porous structure. You have a high voltage that's applied between the emitter and the extractor. And at high enough field strengths, liquid Taylor cones form at the end of these pores and capillaries. And from the tips of these cones, ions and droplets are pulled out and accelerated through the extractor aperture to generate thrust. Now there's a bunch of different types of electrospray propulsion systems out there, and I'll just really focus on ionic liquid ion source, or ILIS. So these types of thrusters utilize a room temperature molten ionic salt fuel, typically either EMI BF4 or EMI IM are pretty typical and common fuels. One of the unique things about this type of ion propulsion is that no neutralizer is required. Due to the chemistry composition of the fuel, you can actually extract both positive and negative ions, which allows you to do self-neutralizing beams as opposed to using an electron source. In addition, no heaters are required, unlike some other types of electrospray like PhET, which uses liquid metal fuel, which allows the efficiency of these particular types of ion thrusters to be very high. They cover a very wide range of ISP depending on the emission mode, so anything from less than 800 seconds to more than 5,000 seconds, at moderate to quite high thrust to power ratios, anywhere from around 14 micronewtons per watt to about 57 micronewtons per watt that's been recently demonstrated in the market. There's a few different types of emission modes. Colloidal, which droplets are emitted, which translates to high thrust and low ISP. You have mixed mode operation, in which both droplets and ions are emitted, and the pure ionic regime, which is the highest efficiency mode, where purely ions are emitted from the thruster, which signifies low thrust but very high ISP. In addition, there's a bunch of different types of emitters used in this technology. The most commonly explored and oldest types are the MEMS silicon-etched hollow capillary arrays, as well as laser ablation micromachined porous glass spike arrays. However, in recent years, there's been a lot of growing interest in macro-scale CNC machined spikes or ridges to really reduce the cost and make this technology more affordable and accessible. So what are some of the advantages of electrospray propulsion at the PocketQube level? Really, if you look at the whole field, there's only a few types of EP technologies that can scale in terms of size, power, performance, and non-pressurized refuel requirements at the PocketQube level. These include pulse thrusters like pulse plasma thrusters and vacuum arc thrusters. MEMS resisto jets are up there, as well as ILIS. So all these types of thrusters have been or are being currently explored in the PocketQube realm. Of the types of thrusters available at this scale, ILIS has been able to demonstrate that it has really the highest combination of thrust to power and ISP levels at this scale. Another benefit is that they have less EMI than pulsed systems, which typically operate with very large current pulses to generate the plasma, since these operate in a more quasi-DC state. They're passively fed fuel, so no heaters or neutralizers are required, and the fuel is stable and safe across a very wide temperature range, and is vacuum compatible and with negligible vapor pressures at high vacuum. Because of the physics of the thruster, you can get extreme miniaturization, everything from single microscopic emitters to large emitter arrays. So this what lends itself very well for all applications, ranging from primary propulsion to attitude control. And depending on how the thruster system is designed, you can get a wide performance range, ranging from low thrust to high ISP to high thrust and low ISP. So here is the current iteration of the Electrospray thruster that I'm developing. This is the AIS 𝗖𝘀1. This is currently the V6 system. So everything you see here is included: the high voltage electronics, the low voltage control, the actual thruster itself, as well as the fuel, which is stored inside. So some specifications of the currently tested V6 prototype. Relatively compact in terms of ion propulsion. It's a 45 by 45 by 16 millimeters. The dry mass is 39 grams of the 1 gram fuel capacity. I'm using a very classic EMI BF4 fuel. The emitter selected was a CNC machined glass ridge emitter, which allowed me a lot of surface area to explore emission while significantly reducing the cost and making it easier to work with. So far, the nominal thrust has been measured at around 0.04 micronewtons with a peak thrust of 0.4 micronewtons, with indirectly measured ISP in the low 4,000 seconds, based on the acceleration voltages of plus minus 5 kV during peak operation. It's also very low power with 5 volts in at less than half a watt of power. So really the core of the design and around 𝗖𝘀 is the porous glass emitters. So for this particular one, this is a CNC machined ridge. The glass is standard chemistry filter frit. So this is a P4 frit, a 25 millimeter diameter disc. The ridge tip is about 0.1 millimeters with a base at 2 millimeters. This isn't really an ideal geometry for emission optimization, but it was the first one that I was able to play around with and explore in developing these thrusters. So in order to further simplify the testing and manufacturing process, I've been working a lot with 3D printed housing for this and other thrusters. So here you can see a few iterations of the thruster. I did try 2 types of 3D printed plastics: the SLA resin prints here on the bottom on the left, and then the FDM Ultim 1010 on the top and on the right. The SLA stuff actually had a lot of issues with arc flashovers and discharge at high vacuum due to the outgassing. But the Ultim has performed extremely well, and there hasn't been any issues in terms of outgassing or high voltage flashovers during operation. So fueling this type of thruster is actually quite simple, but it does require high vacuum fueling. And there are several reasons for having to fuel this type of thruster and other types of electrospray thrusters in high vacuum. For 𝗖𝘀, you need to completely saturate the porous glass. So this allows the liquid to fully saturate into the pores, because this is actually a quite viscous liquid. It allows for fuel degassing as well as porous gas degassing, and baking out and desorption of water from the fuel, just because the fuel can be hygroscopic. So this ultimately improves thruster operation, because if you don't want any air bubbles or water vapor kind of bursting out during operation, which can happen if it's not properly prepared and baked out for operation. So in order to qualify this thruster, there's been significant work done on the electronics. I started out at very first with absolutely no switching on board, just applying single high voltage and working from there and looking at various semiconductor switching. And at this point, I've settled upon a high voltage micro relay, which is used to both isolate and switch the plus and minus 3.5 kV power supplies, which you can see kind of in the center here, the pico supplies, as well as developed a simple high voltage test load for actually testing and qualifying the thruster before actual firing and vacuum. So here you can actually kind of see one of the bench tests that was done before the very first firing test to qualify the thruster electronics. So you can see here it is switching at plus or minus 3.5 kV, kind of stress testing it at higher frequency levels than would be seen in testing, just to make sure the electronics all qualify and check out. So one of the big things that have been done during this development phase, because the ridge machining takes about a few months, 3 to 4 months, one of the easy ways to optimize performance based on the materials I have is changing out the extractor. And there's been a lot of work to optimize the extractor performance. On the left, you can see a standard linear slit extractor. So this was the first one tried, and it was found that early on in testing, there's significant field enhancement right at the corner of the ridge, which would cause excessive emission and premature failure at this point. So the newest iterations actually use a special flared extractor, which reduces the field strength at the corner and eliminates emission here, and focusing the emission in the central region of the thruster to allow better performance. And again, with the extractor, it can also look at the slit widths as well as the thickness. And ideally, I want as high of a field strength at the tip as possible, as well as reducing the beam divergence of the system, so that ways you get higher thrust efficiency, because the more the beam diverges, the more thrust you are losing in the radial direction instead of the axial direction. So in the most recent version, I have a very close emitter with a thicker plate that gives me better field or tighter field divergence on the beam, which you'll actually see in the next upcoming videos, kind of a comparison of the two. So this is kind of the comparison. On the left side, you have the version 5 thruster. So where you have the standard slit, which is about 0.75 millimeters and a 0 millimeter spacing between the emitter and the extractor. And on the right, you have the enhanced extractor currently used in the V6 version. So this is a 0.5 millimeter slit with the flared ends, as well as a 0.1 millimeter distance to help prevent liquid bridging and shorting between the emitter and the extractor. So here you'll actually see a video of the thruster firing. This is with the V5 design. So this is the standard linear slit. So you can actually see the ion beam firing, and right there is the transition between a positive and negative high voltage cycle. So you can see it's a very wide diverging beam, which is not ideal, and that emission is really occurring in one place. So that was kind of the reason to move to the enhanced extractor. You'll also know there was a bit of board flashes here and there during this test, which was completely resolved by adding a few surge protection resistors in the high voltage circuitry, which significantly helps stability. So again, looking at the beam, we have a very wide diverging plume, and looking at the thruster afterwards, you can actually see emission occurs exactly in the corner, with some liquid creep failure that eventually causes the thruster to short. One of the interesting challenges with 𝗖cie is that the high voltage tends to draw the liquid up in very unexpected ways. So you often see in post-test analysis, there's this kind of branching structure shorting between the emitter and the extractor. So moving on, we have the most recent test, the V6 test, with the enhanced slit extractor. So here you actually see now a very much tighter sheet-like beam. So you can see kind of 3 points of emission. So this was actually the first test where multi-site emission occurred in the thruster. So we have emission now across the slit. And although this beam is physically less bright than the prior beam, it put out 2.5 times more beam current. So this was at around 5 microamps measured beam current in the Faraday cup, whereas the prior test was only about 2 microamps of beam current. So again, looking at the beam, we have a very tight focused sheet-like beam. It's a little bit diverging upwards due to probably some misalignment between the optics of the emitter and the extractor. And we can see, looking at the thruster afterwards at the end of life testing, that emission does occur right in the center of the emitter, which is where we want it. And you can also see some of the liquid bridging failure that occurred during testing. So moving forward, the V7 iteration, which is probably going to be the final iteration of this particular development phase, I'm looking at new housing to limit direct paths between the emitter and the extractor, as well as employing a special shield electrode to prevent liquid creep coming up from the base part of the porous emitter disk during peak operation. So actually, these parts literally just came in last night. You can see the new 3D printed housing and the new shield electrode, and you can see one of the ridge emitters installed for fit checking. So I will actually be running this test probably within the next week and gathering data on this new geometry. Moving forward, we have the next development phase, the AIS 𝗖𝘀 1.2. So this uses the same linear ridge geometry, except with a much tighter and narrower ridge. Unfortunately, the ridge that I'm using now is a bit too wide, so the field enhancement isn't really enough to get full beam turn on and as high emission as I'm expecting. But hopefully this will be mitigated moving forward with this new design. And you can kind of see the general structure of the thruster. You have the outer casing, you have the emitter, you have a porous glass reservoir, which is a different porosity that's pushed up against the emitter disk, as well as a contact disk, and then a wave spring that goes on the bottom of here that both mechanically compresses everything as well as provides electrical connection to the board. Finally, the ultimate direction moving forward for this thruster system will be starting with the AIS 𝗖𝘀 2. So this will actually employ a full 2D array of CNC machine spikes. So this allows for significantly larger emission surface. It's a little bit more costly and tricky to machine, but this seems to be the general trend actually moving forward in work done in this field, offering quite high thrust and ISP levels at low powers. So really the aim specs for this thruster will be 1.6 watts at greater than 20 micronewtons of thrust. The ISP is aimed for over 3,500 seconds of ISP, which has been demonstrated already with the 𝗖𝘀 1 operating at plus or minus 5 kV. And with the new thruster, I will also be adding a second control board dedicated to the control and startup sequences of the thruster. Ion thrusters are particularly tricky to operate, and especially with this one, I had to play a lot of tricks in independently switching the high voltage supplies and the relays to keep everything within spec and to operate this thruster at such a high voltage in such a tight space. So here you can kind of see the CAD models of the CNC machine spike arrays as well as fitting into the housing. So kind of beyond this, I also work on other types of thrusters. So this is the AIS GPPT3 1C micro pulse plasma thruster. This was actually the very first fully integrated PocketQube thruster that I built. So you can actually see the thruster here as well as it firing. And this thruster, by the way, all the manufacturing files, all the data, all the test videos and test logs and everything are available for this thruster. So you could actually quite literally go and build this thruster yourself, which is part of the open source initiative of all my thrusters that I do, which will be the same for the 𝗖𝘀 1 once it completes its testing phase. This thruster will actually be flown on the AMSAT Genesis PocketQubes. So these already passed the vibration and integration testing. So we're currently looking at launch, hopefully sometime at the end of the year. So 2 of these thrusters will be launched aboard the Genesis NNL SATs, which will be particularly exciting if they function. And next, moving forward from that, my most recent testing has been with the AIS EPPT1 micropulse plasma thruster. So this is taking lessons learned from the prior thrusters, pulse plasma thrusters, and improving performance. So I recently completed the second ignition testing in the past couple of weeks, and I have new parts in to improve performance. So the third test will actually be done in the next couple of weeks as well. Finally, there's a bunch of other thrusters currently in development, some experimental stuff that are already under initial design. So I'm looking at a solid iodine fueled microresistor jet, the first AIS vacuum arc thruster, the VAT1, as well as a couple of experimental pulsed ion thrusters, the vacuum arc ion thruster, or VATE1, and a pulsed plasma ion thruster conversion from the EPPT1 to the EPPIT1. So thank you for listening to this presentation. You can follow everything that I do on the AIS Twitter and Instagram and YouTube. I do live testing of all the tests, and you can really see the entire design process from initial conceptual CAD models to the full testing and end-of-life qualification. So it really gives people an opportunity to see how these systems are designed and developed and built from scratch. And at the end of each design cycle, I release everything open source so people can access these technologies more easily.